Welcome, and thanks for tuning into my talk on Grafs, Declarative Graph Analytics. My name is Farzin Houshmand, and this is a joint work with Mohsen Lesani and Keval Vora. If you look at the world around you, you'll see that graph applications are everywhere. They are a backbone of important services in different domains such as social networks, search engines, recommendation systems, and even computational biology. Achieving high performance is crucial to these applications. Therefore, they require scalable implementations to process graphs with billions of nodes and edges. There has been a growing number of high-performance graph processing frameworks across shared memory and distributed platforms, such as Lygra and Gemini and Greenmore. However, existing frameworks provide programming models that are low-level and different from each other, making it challenging for the end user to implement and optimize programs. On top of that, there isn't any sort of guarantee about the correctness of programs. Also, existing declarative languages such as Freckle and Elixir require users to write the kernel functions. As an example, BFS is expressed differently in Lygra, GridGraph, and Gemini, which require knowledge about each framework. The goal is to have high-level abstraction for graph analytics, which helps us to write correct and optimized programs. As a solution, I present Grafs. Grafs is a high-level declarative language for graph analytics. It features semantics preserving transformation rules that optimize the program. We have identified three core primitives in graph analytics called iteration, map, and reduce. Grafs is backed with formal definitions of iterative models and their correctness and termination conditions. Having the vision of using automated reasoning to build rigorous systems in mind, Grafs synthesizes kernel functions for iterative models and generates code for 5 high-performance graph frameworks. The workflow of Grafs is as follows. Given the specification of a program, Fusion rule transforms the specification to the three primitives of iteration, map, and reduce. Then the fused form is passed to the synthesis engine to generate correct and construction kernel functions. Finally, given the kernel functions, the low-level implementations for each framework are generated. Grafs supports different classes of graph analytics. First are problems that iteratively calculate values for each vertex, such as Google's PageRank or connected components. Second are traversal and path exploration problems, such as BFS and single source shortest path. And finally, social network analytics use cases, such as calculating radius of a social network or finding trust circle of a user. Generally, these are the algorithms that reduce values over paths, hence we call them path-based graph analytics. Let's go over examples written using Grafs declarative language. Take a look at the specification of single source shortest path rooted at S. The value of vertex V is defined as the minimum weight of all the paths that start from S and ends in V. Another example is the radius. The radius of a graph is defined as the minimum eccentricity over all the vertices, where eccentricity is the maximum distance of a vertex to others. And finally, an interesting social network analytics, least trust. Least trust measures the least amount of trust from a user to a neighborhood in a social network. Given the definition of single source shortest path and widest path, L trust of S calculates the widest path to each vertex within the radius of S. Capacity of paths can represent the trust value from source to destination. Therefore, L trust calculates and returns the narrowest of those paths. I'd like to emphasize on the fact that programs written in Grafs language use mathematical notations, therefore they are concise and as short as possible. Now let's take a closer look at the specification language. The declarative language of Grafs precisely captures path-based graph analytics. Consider the radius example that we just saw earlier. Radius is calculated by getting the minimum eccentricity over a set of sampled vertices. Therefore, in the first step, we need to calculate the shortest path length to all the vertices. This is done by applying minimum reduction function to the result of length path function. We have modeled known path functions such as length, weight, and capacity. Also, the reduction functions are from the known reduction operators. Reduction of these sorts are called path-based reduction and have the general form of applying reduction function R to the result of a path function for a set of paths. We will later see that path-based reductions can be calculated using iterative models. The path-based reduction can also be represented with an islet term that binds the variable x to the result of the path-based reduction at each vertex. Mapping over vertex values can be achieved by combining multiple path-based reductions with binary operators. The map operation in this example is simply the identity function. Next, we need to calculate the eccentricity for all the vertices by applying the maximum reduction function to the shortest path computation. In Grafs, reduction function can be applied to the result of a path-based computation, and it's called a vertex-based reduction. Finally, the minimum of the eccentricities over a set of sample sources are calculated. In Grafs, a vertex-based reduction can be written as a triplet construct. It separates terms for path-based reduction, mapping over vertices, and vertex-based reduction. Later, we see that triplet form is easily implementable using the primitives of graph analytics called iteration, map, and reduce. As for the semantics of Grafs input language, here I present one of the rules. You can find a complete list of the rules in the paper. The rule SP-read defines the denotational semantics of a path-based reduction. At each vertex V, this rule applies the path function to each path to V, and applies the reduction function R to the resulting values. The semantics of Grafs are compositional, and we have formally proved that if two terms are semantically equivalent, replacing one with other preserves the semantics. This lemma is important since compositionality of semantics allows fusion rules to optimize the specification. The next step is the fusion. Executing multiple rounds of path-based reductions sequentially result in redundant operations on edges and vertices. Consider two path-based reductions, the red one and the blue one. Naively, they can execute in sequence. However, same operations would take only one round when fused together. Therefore, the fused version eliminates redundant operations. With that said, fusion is a set of rules that transform the specification to a single triplet by combining similar operations. We have formally proved that fusion transformation is semantics preserving. We have identified three fundamental primitives of graph analytics called iteration, map, and reduce. And fusion converts the specification to these primitives. Generally, there are three types of transformation. First is fusion of the path-based reductions. Second, fusion of mapping operations over the results of path-based reductions. And finally, fusion of the vertex-based reductions. Consider the radius calculation sampled over two sources, S1 and S2. First, the vertex-based reductions starting from S1 and S2 are transformed to triplets separately. In the next step, the two triplets are fused together by creating a pair for path-based reductions and vertex-based reductions. In this example, there is no mapping, so the map expression simply returns the path-based reduction. Then the pair of path-based reductions are transformed to a single path-based reduction that operates on a pair of values with the following path function f and reduction function r. Here, I'm going to take a second to show the fusion rule that is applied in this step. Rule fn pair transforms all pairs of path-based reductions to a single path-based reduction, such that the path function applies a pair of path functions to a path, and the reduction function operates on pairs of values. Finally, the pair of vertex-based reductions are transformed to a single vertex-based reduction R prime that operates on pairs of values. We saw Grafs' specification language and how fusion transforms it into iteration, map, and reduce. Mapping and reduction over vertices can be implemented by a traversal over the vertices. Here we review iterative models. The iterative models are algorithms that calculate path-based reductions. In Grafs, we have formally modeled 9 variants of iterative models with different directions, reduction functions, and synchrony types. All these models are parametric in terms of graph analytics kernel functions. In Grafs, we have defined a high-level language for the kernels. Consider SSSP example rooted at S. Initialization initializes vertices by setting the value of source vertex to 0 and the rest of the vertices to undefined. The propagation propagates the new weight by adding weight of edge E to the current value. And finally, the reduction function aggregates values and returns the minimum weight. Let's consider the pool model with idempotent reduction. The value of the vertex V at iteration k is represented with sk of v. In the beginning, all the values are undefined or bought. The calculation starts by initializing vertices with the initialization function. Now let's consider vertex V in the kth iteration. The active vertex V starts pulling the propagated values from all the incoming neighbors. The value of the vertex V in the next iteration is then calculated by applying reduction function R over the pooled values and the current value of V. Finally, if the value of e changes, the outgoing neighbors are set to be active for the next iteration. The iterations continue until the value of all the vertices stay unchanged. The correctness of the iterative models depend on a set of correctness conditions for each kernel. Here I only highlight a subset of conditions. The conditions for the reduction function are straightforward. R must have the following properties: identity, commutativity, associativity, and idempotency similar to the iterative model. Given a path-based reduction that starts from the source S, the correctness condition for initialization requires the value of the source vertex S be equal to the result of applying the path function to the initial path with M0, and the rest of the vertices to be undefined. The condition aggregate propagation is the crux of conditions for propagation function. This condition states that reducing the path values of P1 and P2, the local propagation of the result along the edge E should be the same as reduction of the global calculation of the path values for two extended paths P1E and P2E. Therefore, the condition checks for the following equality for the propagation function. Using the correctness conditions, we have formally proved the correctness and termination of the 9 variants of iterative models. For example, the correctness of the synchronous pole idempotent model states that if all the correctness conditions for the kernel functions are satisfied, at the end of kth iteration, the value that the model calculates complies with the specification. We have reviewed the correctness conditions for the kernel functions. Now let's see how they are used to synthesize the kernels. To synthesize kernel functions of a path-based reduction, Grafs uses syntax-guided enumeration on the grammar of the kernel functions to generate candidate programs. Then the validity of each candidate is checked against the correctness conditions using the Z3 SMT solver. We have modeled the Grafs path functions and relations in the combination of the quantified uninterpreted functions and list theories. The output of the synthesis engine is then correct by construction kernel functions. Now I'm going to wrap up the presentation with a highlight of the experimental results. All the experiments are done on a 4-node cluster. Grafs can generate code for LiveGraph, GridGraph, Gemini, PowerGraph, and Graph at runtimes. This table here shows the list of the use cases that Grafs successfully synthesized. We observed that Grafs can generate each use case efficiently in less than 2 minutes. Also, comparing lines of code written for each program in different frameworks versus Graph specification language shows that programs written in Grafs are significantly smaller. Our first set of experiments are to show that fusion leads to fewer number of operations. To do that, we have collected the ratio of the processed edges in the generated programs over unfused implementations for 3 programs. The results indicate fusion reduces number of edge operations by up to 75%. Also, the reduction in number of edge operations translates to up to 4 times speedup across different frameworks. Finally, after studying the scalability of the fused programs in the LiveGraph framework with increasing number of cores, we observed that the speedup with respect to the handwritten programs remained steady, and the fused programs scale similar to the handwritten ones. In the conclusion, fusion preserves the parallelism of the specification and never rely on major synchronization bottlenecks such as locks. Wrapping things up, I presented Grafs, a high-level declarative language for graph analytics. It features semantics preserving optimization rules. We have modeled iterative reduction models and their correctness conditions. Using the correctness conditions, Grafs synthesizes kernel functions, and finally our results on fused programs showed up to 4 times the speedup compared to the handwritten implementations. Thank you all for watching.